Alright, so we saw how spectral lines can be a third way of finding the temperature of a star. But we can also use these dark spectral lines to figure out the chemical composition of the sun and other stars. Spectroscopy is really what turned astronomy from basically astronomy into astrophysics. We could actually, from a very great distance, talk about what things in the universe were made out of because of spectroscopy. Now, it's not easy because, as you see, for example, it looks like stars that are around 11,000 degrees have more hydrogen than stars that are 5,000 or 6,000 degrees. That is not true. It also looks like the sun, which is a G star, or let's say a K star, a cooler star, has way more sodium than it has hydrogen. That's not true either. So, but astronomers and spectroscopists are very clever. They know how these spectral lines behave. They know that they're temperature dependent. And once we solve for temperature, we can then work backwards to figure out the abundances. And it turns out that sodium is a very, very tiny fraction of the gases that are in cool stars, the sun and cooler, even though that their lines are very prominent. Okay, so we're not really going to talk very much about chemical composition because basically it's so complicated, it's well beyond the level of this course. All we're going to say is that it's done by the analysis of these dark spectral lines that we just saw. We assume that the elements in the star's atmosphere, which is where those absorption lines are formed, are the same as the interior, because a star is made 100% of gas, and mostly ionized gas at that. And it's also very difficult. That's the reason this is the only page of notes you're going to have on this process. Because the strength of the spectral lines depend both on how much of the gas is there and also on temperature, it makes it really tough to figure out the total abundances. But again, astronomers, spectroscopists, very, very clever people, and they've done a good job of being able to do that. Okay. Well, that brings us to the third property of a star that we can determine, and that is the energy output or luminosity of a star. Okay, luminosity is a measure of the intrinsic brightness of the star. Now, by intrinsic, I mean something that is tied to the star's actual character. Okay, something that's not dependent on another property, like, for example, its distance. Okay, so one of the amazing things we have found out about stars, and there are many amazing things, but the one that gets me the most is the range of luminosities, the range of brightnesses of stars. What we do is that because stars have such bright energy outputs, so for example the sun, the luminosity of the sun is 4 times 10 to the 26th watts. I mean, that's just an immense amount of energy. You can't even imagine that amount of energy. And so if I told you that another star had 5 times 10 to the 28th watts, would that be a really bright star? Well, unless you remembered that our sun had this many watts, it would be really hard to figure that out. So what we do is we say, okay, this symbol here, this little circle with a dot means the sun. We're going to use that as a unit. We're going to say 1 solar luminosity is equal to 4 times 10 to the 26 watts. And so if you had a star that was 8 times 10 to the 26 watts, you would say that that star had 2 solar luminosities because it was twice as bright as this. Okay? So what we do is we say, okay, this is going to be our fundamental unit of a star's brightness, a solar luminosity, and we are going to talk about the brightness of other stars as multiples or fractions of the sun's luminosity. And the amazing thing is, the brightest stars in our sky are as bright as approximately 100,000 suns. So the luminosity of the most luminous stars in our galaxy, the real show-offs of our galaxy, are as bright as 100,000 suns. Now imagine 100,000 suns all in one place. That is exactly how bright the brightest stars in our galaxy are. Also, however, the Sun is actually a fairly impressive star because the luminosity of the least luminous stars, and there are a lot more of those than there are the really, really bright guys. The least luminous stars in our galaxy are about 1/10,000th as bright as our Sun. So in other words, you would need 10,000 of these to equal the brightness of one Sun. And nature makes way, way more of these stars than these. Okay? If you compare the dimmest stars in our galaxy to the brightest, the multiplier you would have to do to get from the dimmest to the brightest is a factor of 1 billion. So in other words, these very common, very, very low luminosity stars, you would need 1 billion of those to equal the brightness of one single brightest star in our galaxy. And that always just amazes me, that there's such an incredible range of brightnesses, stellar brightnesses, within our galaxy and within other galaxies for that matter as well. Now, when we look into the night sky, the stars we see are generally the show-offs of the galaxy, the ones that maybe aren't this bright, but are fairly bright. And that's because, of course, stars look dimmer the farther away they are. Okay? The apparent brightness, as opposed to the intrinsic brightness of the star, the apparent brightness is a measure of how bright a star appears to us. When we look into the sky, the star's apparent brightness is all about how it appears to us. And that, of course, depends on two things. It depends on how bright the star is, but it also depends inversely on distance. And not just on directly on inversely on distance, but inversely as distance squared. You may remember that term from our talk about gravity earlier on in the course. Okay. So the apparent brightness, we'll use lowercase b for apparent brightness, is inversely proportional to the distance squared. We use r for distance again because we usually talk about a radial distance. Unlike gravity, however, it's a little bit easier to understand why this is the case. A good analogy is a can of spray paint. If you can think of the photons of light being given off by a star, just like little blobs of paint being spit out of a can of spray paint, you would see that if you had a surface a particular distance away, it would be covered with a certain amount of paint. Okay. If you took another surface and put it 2 units of distance farther away, okay, in other words, twice as far away, that same paint would cover not twice the area, but it would cover 4 times the area. If you put the surface that you were spraying 3 times as far away as our original surface here, you would see that it covers not 3 times the area, but 9 times the area. And if you put it 4 times as far away, it would cover 16 times the area. Okay? So the point is, the brightness would be similar to how thick the paint is on each of these surfaces. So for example, the paint would be really thick on this surface, but every square on this surface, well, there are 9 times as many squares that it's catching the same amount of paint, so the thickness of paint would be 1/9 the thickness as it is here. And here, the paint would be 1/16 the thickness. Okay? That's what the inverse square law is all about. Basically, the paint spreads out inversely with the square of the distance so that it covers, the square of the distance area more, the same amount of paint. So that means it would be 1 over the distance squared as intense. Now, in the case of light, if this were a light bulb instead of, or a star, for example, instead of a can of spray paint, and if these were photons entering your eyeball instead of paint covering a surface, it's the same sort of thing. The same number of photons that would enter your, let's say this is a telescope mirror, the same photons that would hit the telescope mirror here would be spread out over 4 times the area here, so each square would only get 1/4 as much light. Here it would be spread out over 9 times the area, so each square would only get 1/9 the light. Here it would be spread out over 16 times the area, so each square would only get 1/16 the light. And since our telescope is the same size no matter how far we put it away, or our eyeball, our iris, is the same size no matter how far we put it away, that means that the light would be 16 times dimmer, or 1/16 as bright, when we get this far. Okay? So for example, if this were the sun and this were the distance of the Earth, if we had a planet that was 3 astronomical units away, in other words, 3 times as far away as the Earth is from the sun would look 1/9 as bright from that distance. Okay? Because the sunlight would have spread out over 9 times more area than it does when it reaches the planet Earth. Okay? And here's another drawing of this sort of thing. Okay? Here we have a brighter patch because all of the star's light at this distance is going through this square. By the time it gets twice as far away, the same amount of light is covering 4 squares, so it's much dimmer, it's 1/4 as bright, and by the time it gets out to here 3 times as far away, it covers 9 times the area, and so each patch would collect 1/9 as much light. Okay. So as the light moves away from the star, it spreads out over a larger and larger area, okay, and so seems to get dimmer and dimmer. One more image here, and this time the red lines represent rays of light or photons of light. So we can say that the apparent brightness of a star is just the star's luminosity, L, divided by the area of a sphere with a radius, R, equal to the star's distance. So this would be the actual equation for the apparent brightness of the star, sometimes called the flux that we get from the star. Okay. So now, if we're working backwards, if we're somewhere at this distance, and the star is over here, and we collect a certain amount of light from a star, because that's what we get when we look up into the night sky, we only see the star's apparent brightness, how can we figure out how bright the star actually is? Well, to figure out how bright the star actually is, we want to know L. If we know B, we can measure that with our eyes or with a camera. We have to know R. We have to know the distance. And so the only way to determine the brightness of the star is to figure out its distance. The only way to directly do that. And the method we use is called geometric stellar parallax. Okay, your eyeballs do this automatically. You get depth perception because we have 2 eyeballs. And because of that, we can judge how far away nearby objects are. Okay? Well, stars are way farther away, so our eyeballs do no good. But what we can do is we can pretend that the Earth on this side of the sun is 1 eyeball, and then 6 months later we take a picture from the Earth on this side of the sun, which would be the other eyeball, and we would see this nearby star shift its position ever so slightly with respect to really, really distant stars. And the bigger the shift, the bigger the jump back and forth on our photographic plate, the closer the star is. And the smaller the jump, the farther the star is. And in fact, if you use a distance method called parsecs, a distance unit called parsecs, you get this very, very simple equation here. The distance in parsecs is 1 over the parallax angle, which is this angle, the amount that it jumps, in arc seconds. Okay, an arc second is a tiny, tiny angle. It's 1/60th of 1/60th of a degree. So it's a 3600th of a degree. Okay, most stars in our sky have a parallax smaller than that. Okay, parallax is the only direct measure of a star's distance. There is no other way to directly measure a star's distance. Okay. This unit of distance called the parsec is one of my pet peeves because I think astronomers were just very lazy in figuring out the parsec. 1 parsec is equal to roughly 3 1/4 light years. So basically, if they took this equation and put 3.26 on top, the distance would have been in light years, which is a much more conceptually meaningful unit of distance. Okay. At any rate, that's the end of part 3. We will continue part 4 next.